These are the solutions to your optimization quiz. All right, starting with question number 1. We are maximizing area, so our primary equation will be that of the area of our rectangle. Our secondary equation is given to us. So we've got a relationship between x and y, so we will rewrite A. I'm going to write it in terms of x. So we've got 6 minus x over 2. And then I think I want to write this as, let's say, 6x minus x squared over 2, which is just 3x minus 1/2 x squared. So now let's go ahead and find our critical numbers. So our derivative looks like this, and x equals 3 is our only critical number. Now from here we've got a choice between the first derivative test and the second derivative test. And just because I have a nice polynomial, I am going to use the second derivative test. So a double prime is equal to -1. So since a prime of 3 is 0, and a double prime of 3 is negative, that's an and, we can say a of 3 is a local maximum. Now the questions ask us for the dimensions, so since we know that x must be equal to 3, here we've got x must be equal to 3. Y we can find by using our secondary equation. So I'm going to come back up here and I'm going to say y is equal to 6 minus 3 over 2, which is 3/2. So my statement here is the dimensions of the rectangle with maximum area are x equals 3 and y equals 3/2. Okay, question 2. We have our box with a square base and an open top, and we want to minimize surface area. So our surface area, let's see, I'm going to call these x and the height y. So that means that our surface area would be x squared, and then we've got 4 sides with an area of x times y. Now we need a secondary equation. Our secondary equation would be that the volume is 4 feet. So x squared y is 4, which means that y is equal to 4 over x squared. I'm going to use that information in my primary equation and substitute that y is now 4 over x squared. So we have 16 over x as our term here. So now let's take our first derivative. I'm going to get 2x minus 16 over x squared. And I think I'm going to rewrite that as 2x cubed minus 16 over x squared. Now we find our critical numbers. Our derivative is undefined when x is equal to 0, but I'm not going to use that information because I don't want a dimension of 0. So I'm just going to look at where our derivative is equal to 0, and that happens when x is equal to 2. And now we have a choice between doing the first derivative test and the second derivative test. I'm finding the second derivative easy to find. So the second derivative is 2 plus 32x to the negative 3. So the second derivative at 2 is going to be 2 is 6. All right. So now we'll write our answer, the dimensions that require the least material are x should be equal to 2 feet. And if we come back here, if x is equal to 2 feet, then y must be equal to 1 foot. And that's it for number 2. All right, number 3, we've got our page with 24 square inches of print, and the margins at the top and bottom are 1.5 inches, and the margins to the left and right are 1 inch. So I'm going to call this dimension y, and that dimension x, which means that x times y must be equal to 24. So that's our secondary equation. Our primary equation is the area of the whole page. So the area of the whole page would be y plus 3 times x plus 2. So we'll do a little substituting here. Y is equal to 24 over x. If we distribute, we get 24. That's a 48. Plus 3x plus 6. So there's our primary equation in one variable. I'm going to find the critical numbers first by finding the second derivative, or the first derivative. I get negative 48x to the negative 2 plus 3. I think I want to write that differently. I'm going to write this as 3x squared minus 48 over x squared. So again, we're looking at a situation where our first derivative is undefined when x equals 0, but that's not in our domain. We don't want our x dimension to be equal to 0. So let's just look at where the derivative is equal to 0. So that happens when x is equal to 4. Again, we'll reject the negative because we don't want a negative dimension. Again, I'm going to use the second derivative test. And I've got a double prime is 96x to the negative 3, or 96 over x cubed. And a double prime of 4 is 96 over 4 cubed, which is definitely positive. So we can say since a prime of 4 equals 0 and a double prime of 4 is greater than 0, we've got our minimum. So now we'll say to use the least amount of paper the dimensions should be, we want x to be 4 inches, and if x is 4 inches, we know that y must be 6 inches. Okay, last question, number 4. We're told that the sum of two positive integers is 90. So that's got to be our secondary equation. And then we've got the product of one integer and the square of another is a maximum. So this is our primary equation. I'm going to call it P for product or primary. And we need that in one variable. So let's use the secondary equation and rewrite this. I'm going to say that this is 90 minus y times y squared. Okay, so now we've got our primary equation in one variable. Going to look for critical numbers. P prime is 180y minus 3y squared. We set this equal to 0. I get 60 minus y. Now algebraically I get that y is equal to 0, but they specify that our integers must be positive. So I'm going to reject that and just look at when y is equal to 60. And again, I think I'm going to use the second derivative test. The second derivative is 180 minus 6y I get negative 180. Okay, so that's good news because we can say so we have our local maximum. So one integer must be 60. That means that the other integer must be 30. But we're asked only for the greater integer, so we say the greater integer is 60.